A fluid is any matter that has tendency to flow. All liquids and gases are together referred to as fluids. Solids and liquids have a fixed volume, while volume of a gas depends on the volume of its container. However, when an external force acts on certain categories of bodies, their volume changes and the bodies develop a restoring force. The restoring force acting per unit area is called stress. Change in volume due to stress is negligible in solid, very small in liquids, and very large in a gas. Liquids are 10 to the power 5 times less compressible than gases, but are about 10 times more compressible than solids. This is because the molecules in a liquid are not as closely packed as in a solid, but are closer to each other as compared to a gas. Another common physical quantity related to fluids is pressure. Pressure is defined as force exerted per unit area. We experience so many incidents involving pressure in our day-to-day life. One such example is that it is easy to drive a sharp nail into a wall than a blunt one. This is because, for a sharp nail, the area on which force acts is less, hence, more pressure. Here, the force exerted on the nail is perpendicular to the surface on which it is applied. Similarly, the force exerted by a fluid on an object submerged in it is always perpendicular to the object's surface at all points. This is because if there were a force parallel to the surface of the object, then, according to Newton's third law of motion, the object would resist the force in the opposite direction, which would cause motion of the fluid along the surface of the object. However, the fluid is at rest. Since there is no flow of fluid parallel to the surface of the object, we can conclude that the force exerted by the fluid at rest is not parallel but normal to the surface of the object at all points. The normal force exerted by the fluid at a point can be measured by the device as shown in figure. It consists of an evacuated chamber with a spring that is calibrated to measure the force acting on the piston. The inward force exerted by the fluid on the piston is balanced by the outward force due to the compression of the spring, which is measured by this device when placed inside the fluid. Let us now learn how to determine pressure. If F is the magnitude of the normal force acting on the piston of area A, then the average pressure, PAV, is defined as the normal force acting per unit area. In limiting case, that is, if small area of the piston is considered arbitrarily, then the pressure is represented as P is equal to delta F by delta A as delta A approaches to 0. The magnitude of pressure does not change with direction. Hence, pressure is a scalar quantity. Dimensional formula of pressure is the ratio of dimensional formula of force to that of area. Dimensional formula of force is mLT power minus 2. Dimensional formula of area is L power 2. Hence, dimensional formula of pressure is mL power minus 1 T power minus 2. Similarly, the SI unit of pressure is the ratio of SI units of force to that of area, which is Newton per meter square, which is also referred to as Pascal or PA. Pressure is commonly expressed in atmosphere, symbolically written as ATM. Atmosphere is defined as the pressure exerted by the atmosphere at sea level, which is equal to 1.013 multiplied by 10 raised to the power 5 pascals. Another important physical quantity related to fluids is density. Density is represented by Greek letter rho. Density of a substance gives a fair idea of its heaviness. It is defined as mass per unit volume. Density of a fluid of mass m occupying volume v is represented as the ratio of m to v. As mass and volume both are scalars, density is scalar and its dimensions are ml power minus 3. In SI system, density is measured in kilograms per cubic meter. Density of a liquid is almost considered constant at all pressures, as it is largely incompressible. However, gases exhibit huge variations in the densities at different pressures, as they are compressible. As it is not always possible to remember the density of materials with their true units, generally we refer to relative density. Relative density is the ratio of density of the substance to the density of water at 4 degrees Celsius. For example, relative density of aluminium is 2.7. Relative density is a scalar quantity. It does not have units as it is the ratio of similar quantities and thus it is a dimensionless quantity. The pressure on an object submerged in a liquid is independent of the area of cross-section. Consider a liquid in a cylindrical container. Now, consider a cylindrical element of the liquid with base area A and height h in it. Let mg be the weight of the cylindrical element. Let 1 and 2 be points on the flat surfaces of the element at its top and bottom. The force due to the liquid pressure on the top surface of the fluid element is P1A, acting in the downward direction, while at the bottom it is force P2A acting in the upward direction. Then, since the liquid element is static, the net force acting on the element in the vertically upward direction should be equal to the weight of the element. But the mass of the cylinder is equal to the product of its density, rho, and its volume, V, or the product of its density, rho, area of its base, A, and its height, h. Substituting equation 2 in equation 1, we get P2 minus P1 is equal to rho Hg. Thus, the pressure exerted by a liquid column of height h is independent of area of cross-section. The liquid also experiences pressure on its free surface. This pressure exerted by the atmosphere is called atmospheric pressure, is denoted by Pa. If point 1 of the liquid element considered is on the top surface of the liquid and is exposed to the atmosphere, then the pressure at the bottom of the element becomes P equals Pa plus rho Hg, where Pa is atmospheric pressure. Here, the pressure difference, P minus Pa, is called the gauge pressure at that point. This gauge pressure thus depends on the density of the liquid, the height of the liquid column, and the acceleration due to gravity at the given place. Thus, at a given height, the gauge pressure is the same at all points at the horizontal level. Let us consider an activity that confirms this concept. Consider various vessels of different areas of cross-sections connected at the bottom by a horizontal pipe. When a liquid is poured through the opening of a vessel, we observe that the liquid occupies the same level in all the attached containers. The level of liquids, H, in all the containers is the same though they contain different volumes of liquid. This proves that the liquid pressure is the same at all points at the same horizontal level or depth. Similarly, the atmospheric pressure at any point is equal to the weight of a vertical column of air of unit cross-sectional area extending from that point to the top of the Earth's atmosphere. Atmospheric pressure is measured in terms of a vertical column of mercury, whose pressure at its bottom is equal to the atmospheric pressure. The greater the atmospheric pressure, the greater the vertical height of the mercury column. The device used to measure atmospheric pressure is called a barometer. Torricelli devised a mercury barometer. For this barometer, a long glass tube closed at one end is filled with mercury and then inverted into a glass trough containing mercury. The mercury column in the tube falls to some extent and a vacuum is created in the tube. This vacuum is known as the Torricelli vacuum. The height of the level of mercury in the tube is nearly 76 centimeters or 760 millimeters above the free level of mercury in the trough, which is equivalent to 1 atmosphere. There are different units of measurement for atmospheric pressure. It can be measured in millimeters or centimeters of mercury column in the barometer. Or Torricelli's. 1 Torricelli is equal to 1 millimeter of mercury column. or in Newton per square meter or Pascal in SI, or dyne per square centimeter in the CGS system, or in bars. 1 bar is equal to 10 raised to the power of 5 pascals. Another device we use to measure atmospheric pressure is an open tube manometer. It consists of a U-shaped tube, which is filled with a low-density liquid such as oil for measuring small pressure differences, and high-density liquids such as mercury for measuring large pressure differences. One end of the tube is open to the atmosphere, while the other end is connected to the vessel whose pressure is to be measured. The pressure P at point A is equal to pressure at point B, which is P equals PA plus rho Hg, where rho is the density of the liquid, g is the acceleration due to gravity, and h is the manometer height, which is the difference in the height of the liquid in both the limbs of the manometer. Here, the gauge pressure P minus PA is equal to rho Hg. Why is gas not used in a manometer? We know that the pressure is the same at 2 points on the same level on both limbs of the manometer, which contains a fluid. For a given change in pressure, the variation in density of a liquid is negligible, whereas for the same change in pressure, the density of a gas varies a lot. This makes liquids largely incompressible. This is why we use only liquids to measure pressure in a manometer. What happens to an object when it is put in still water? Will it float or will it sink? We can determine this with the help of Archimedes' principle. Archimedes' principle states that when a body is partially or completely immersed in a fluid at rest, the fluid exerts an upward force of buoyancy, which is equal to the weight of the displaced fluid. Consider a very small element of fluid in the form of a right-angled prism, ABCDEF, inside a fluid at rest. As the element is very small, every part of it is considered at the same depth, and hence the effect of gravity is the same at all points of the fluid element. We know that the force exerted by the rest of the fluid on the element is normal to the surface. Let Fa, Fb and Fc be the normal forces acting on the 3 rectangular surfaces of the prismatic element. AA, AB and AC represent the areas of the faces BEFC, ADFC and ADEB of the element respectively. PA, PB and PC represent the pressures acting on the areas AA, AB and AC. Geometrically, in the right-angled triangle ABC, BC is equal to AC cosine theta and AB is equal to AC sine theta. The forces shown are normal to the respective areas that include the sides. Thus, we have FB sine theta is equal to FC and FB cosine theta is equal to FA. Let us call this equation 1. As the thickness of the prismatic element FC is constant, the areas of the three sides of the prism can be expressed in terms of the trigonometric ratios as shown for the forces given by equation 2, which is AB sine theta is equal to AC and AB cosine theta is equal to AA. Dividing equation 1 by equation 2, we get FB divided by AB is equal to FC divided by AC, which is equal to FA divided by AA. However, the ratio of force to area is equal to pressure. Thus, PA is equal to PB, which is equal to PC. Hence, we can conclude that the force against any area within a fluid at rest and under pressure is normal to the area irrespective of the orientation of the area. The pressure exerted at a point by a fluid at rest is equal in all directions. Hence, pressure is a scalar even though it is in the ratio of force, which is in general a vector to area. This is what Blaise Pascal postulated as Pascal's law. Pascal's law states that when external pressure is applied at a point in a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. Let us understand it in detail using an activity. Consider a spherical vessel containing 4 cylindrical tubes A, B, C and D of area of cross-section A, 2A, 3A and 4A. Each of these openings is fitted with an airtight piston. Let piston A be pushed with a force F. Then the pressure on the piston is F by A. Pistons B, C and D move out due to this pressure. However, pistons B, C and D can be held in their position only when the forces applied on them, that is, FB, FC and FD are equal to 2F, 3F and 4F respectively. Then the pressure acting at B, C and D is 2F by 2A, 3F by 3A and 4F by 4A respectively, where each is equal to F by A. This experiment demonstrates that the pressure is transmitted undiminished in all the directions, which proves Pascal's law. A number of devices such as a hydraulic lift, hydraulic press and hydraulic brakes work according to this law. Let us look at each of them in detail. A hydraulic lift is used to lift or support heavy objects. It consists of two cylinders fitted with airtight pistons of varying cross-sectional areas. The two cylinders are connected to each other with a horizontal pipe, where the container is filled with an incompressible liquid. The load to be lifted is placed on the piston of larger cross-sectional area. A2. Let a downward force F1 be applied on the smaller piston A1. According to Pascal's law, this pressure F1 divided by A1 is transmitted equally to the piston, where A1 is the area of cross-section of the smaller piston. As this pressure is transmitted equally to the large piston, the upward force F2 acting on the load is equal to the product of the pressure and area of cross-section of the larger piston A2. As A2 is greater than A1, we have F2 greater than F1. Thus, with a very small force, heavy objects can be lifted using a hydraulic lift. The work done by the smaller force is equal to the work done by the larger force, as the displacement of the smaller piston is greater than that of the larger one. Here, the force F1 applied on the smaller piston is called the effort, and F2, the force required to lift the heavy object, is called the load. By definition, the mechanical advantage of a machine is the ratio of load F2 to effort F1. Substituting F2 with PA2 and F1 with PA1, we get the mechanical advantage as A2 by A1. Hence, we can write the mechanical advantage of a hydraulic lift as the ratio of the cross-sectional area of a larger piston to that of a smaller piston. Let us now study a hydraulic press. A hydraulic press is a mechanical machine used to lift or compress large loads. The schematic representation of a hydraulic press that works on force applied manually is as shown. In this machine, a smaller force applied on a column of liquid is converted into a much larger force acting on the load placed on another column of the liquid, connected to the first column. A hydraulic press consists of two cylinders, C1 and C2, fitted with pistons P1 and P2, and valves V1 and V2 connected with tube T1. Tube T2 connects the cylinder C2 with a water reservoir through a release valve, RV. Piston P2 is a platform at the top of which the substance to be compressed is placed. Piston P1 is raised upwards by the application of force F, at the handle edge of the lever. Upon the action of the handle, the valve V1 opens. The water from the reservoir is sucked into the cylinder C1. During this process, valve V2 remains closed. When piston P1 is pressed down, valve V2 is opened. Valve V1 is closed and the water is pushed from cylinder C1 to cylinder C2 through T1. Due to water pressure, piston P2 moves up, compressing the load between the platform P and the rigid ceiling. To release the pressed substance, the release valve RV is opened to allow the water back to the reservoir. Another device that conforms to Pascal's law is a hydraulic brake used in automotives. A hydraulic brake consists of a master cylinder M, filled with brake oil and provided with an airtight frictionless piston P. Through a lever system, the piston is connected to the brake pedal F. Through a tube T, the master cylinder is connected to a wheel cylinder C, consisting of two pistons P1 and P2, which are connected to brake shoes S1 and S2. The same system is connected to the other wheels of a vehicle. When the brake pedal is pressed, the lever system operates, transferring the force to the piston P. The piston P is pushed inward, increasing the pressure in the master cylinder. According to Pascal's law, this pressure is transmitted to pistons P1 and P2 in the wheel cylinder. These pistons force the brake shoes S1 and S2 to move away from each other, which in turn press against the inner rim of the wheel. Hence, the brake works and retards the motion of the wheel. When the pressure is released, the brake shoes return to their normal positions with the help of a spring mechanism.